Welcome everyone. Today we are going to explore something that might sound like science fiction, but it is actually becoming a practical reality in the world of databases, the quantum computing. Now, before your eyes glaze over thinking this is going to be too theoretical, I want to assure you that we are going to focus on real concrete applications that actual companies are experimenting with right now. This is not about replacing everything we know about databases overnight. It is about understanding where quantum computing might genuinely help us solve problems that have plagued database administrators for decades. So, this lecture is lecture 13, Marshall University. This is Professor Atif Farid Mohammed. Quantum computing in database management systems. So think of this session as your practical guide to cutting through the hype. We'll look at where quantum computing actually fits in database management, what its real limitations are, and most importantly, what you can do about it today. By the end of this lecture, you will understand why some of the smartest people in tech are taking quantum computing seriously for databases, while also knowing exactly where to be skeptical. So let's dive in. So let me start with something every database professional knows all too well, and that is disappointment. You write what should be a simple query, you know that data is indexed properly, you have followed all the best practices, and yet it crawls along taking minutes instead of seconds. Or the query optimizer makes a bizarre decision, choosing a nested loop join when a hash join would clearly be faster. These are not edge cases, they are daily realities that cost companies millions in wasted compute time and frustrated users. We have spent decades trying to make these disappointments rarer. We have built smarter optimizers, better indexers, faster hardware, more sophisticated statistics collection, and it works until it does not. The fundamental problem is that some database challenges are at just their core combinatorial search problems. When your database needs to join 20 tables, there are literally more possible join orders than there are atoms in your body. Around 10 to the power of 20 different ways to execute that query. Classical systems use clever shortcuts and heuristics because checking every possibility is physically impossible. This is where quantum computing enters the conversation, not as a magic solution, but as potentially better way to navigate these massive search spaces. Amazon Query Optimizer explores 10 raised to the power 20 plus possible join orders for complex queries. That is one of the solutions. So let's get clear on something fundamental. Databases do two very different kinds of work, and quantum computing is only interesting for one of them. The first type of execution, the actual mechanical work of reading pages from disk according in terms of decoding columns, hashing keys, sorting data, and all the other deterministic operations that turn a query plan into results. This work maps beautifully to modern CPUs, GPUs, and SIMD instructions. It is arithmetic, it's memory bandwidth, it's well understood, and quantum computers offer absolutely nothing here. If someone tells you quantum will speed up your table scans, they are selling snake oil. The second type of work is optimization, the decision making that happens before execution even starts. Which join order should we use? Which indexes should we build? How should we partition this massive table across servers? What queries should we run now versus queue for later? These are search problems under constraints and the number of possible choices explored combinatorially. This is where quantum methods become genuinely interesting. Not because they are universally faster, but because quantum algorithms are specifically designed to explore large search spaces in ways that classical heuristics can't go. Remember this distinction throughout our discussion. Quantum computing targets the planning layer, not the execution layer. Here is the single most important thing to understand about quantum computing and databases, and I am going to put it as plainly as possible. Quantum hardware is not a faster CPU. You cannot take your existing database, swap in a quantum processor, and watch your queries run 10 times faster. That is not how any of this works. Execution, the actual arithmetic and memory operations that process your data, is fundamentally classical work, and classical computers do it extremely well. Quantum computers are specialists, not generalists, and data processing is not their specialty. What quantum computers might actually help with is optimization, the search under constraints that happen in your query optimizer, your physical design turner, your workload scheduler. These systems are constantly making choices. Should I use this index or that one? Should I join these tables first or start with those? Given my memory budget, which queries should I run concurrently? The search spaces for these problems are enormous. The classical systems survive by using educated guesses and pruning aggressively. Quantum methods offer a different approach to navigating these spaces. That's the real opportunity, and that's what we'll focus on. Quantum as a tool for better decision making, not faster execution. So, quantum speed up explained in a little bit more depth here. When people say quantum is faster, they usually mean one of three different things, and it is crucial not to mix them up. First is asymptotic speed up. This means the algorithm's growth rate is fundamentally better. For example, Grover's algorithm can search an unsorted database with a square root speed up over classical approaches. That sounds modest, but for huge search spaces, it can be the difference between impossible and feasible. Second is constant factor speed up, same growth rate, but fewer actual steps in practice. Third is parallelism. Quantum computers can, in a sense, explore many paths simultaneously, though this is often oversimplified in popular explanations. Here is why this matters for databases. This speed up only applies to specific types of problems with specific structures. Quantum does not make everything faster, it makes certain searches faster. When we talk about join ordering for a query with 20 tables, where we are looking at 10 to the power of 20 possible plans, the structure of that search problem might be amenable to quantum approaches. But notice the careful language, might be amenable to. We are not talking about guarantees here. We are talking about matching the right tool to the right problem structure and understanding that no single approach, quantum or classical, wins everywhere. So the real world impact is join ordering for 20 tables query is equal to 10 raised to the power 20 candidate plans. Let me introduce you to QUBO, quadratic unconstrained binary optimization. That is a mouthful, but the concept is straightforward. You represent every decision as a binary variable 0 or 1, yes or no. Should join A happens before join B? That is a binary choice. Should we create this index? another binary choice. Should we partition this table by customer ID? Once again, binary choice. Once you have encoded all your decisions this way, you define an objective function that measures how good a particular set of choice is, and you add penalty terms so that invalid solutions become expensive. Then you hand this formulation to a solver that tries to minimize the total cost. This is exactly the kind of problem quantum annealers are designed for, and it maps naturally to many database optimization challenges. For example, D-Wave Systems worked with Volkswagen on traffic flow optimization using quantum annealing, routing vehicles through city streets to minimize congestion. The parallels to database workload routing are obvious. You have queries that need resources, you have constraints on memory and GPU, and you want to minimize total latency while avoiding bottlenecks. The quantum annealer explores the space of possible schedules differently than classical optimizers. It is not guaranteed to find the global optimum. That is why we call it a heuristic, but for certain problem structures, it can find good solutions faster than classical approaches. So the concept 3 is the data loading tax. Here is the reality check that kills most ambitious quantum database proposals. Even if you have a quantum solver that is genuinely faster, you still have to get your problem into it and get the answer back out. That means building a model with all your costs and constraints, encoding it into whatever format and quantum solver accepts, running the solver, decoding the result, and validating it against your actual operational requirements. Each of these steps takes time and introduces potential errors. If this overhead is larger than the speed up you gain from the solver, you have lost before you started. This is why the most plausible quantum applications in database says focus on the control plane, not the data plane. Control plane meaning planning, tuning, scheduling, configuration, things where you are working with metadata and statistics, not raw data. Data plane means scanning and joining actual rows, things where you need the real data in hand. If someone proposes encoding millions of rows into quantum states for processing, you should be extremely skeptical. The overhead of loading data into quantum form almost always exceeds any theoretical speed up you might gain. But if you are optimizing which indexes to create based on workload statistics, that is metadata. That's manageable, and that's where quantum might actually help. So join ordering is the poster child for quantum database optimization, and for good reason. It is both critically important and brutally hard. When you join multiple tables, the order you join them in can make a 10,000-fold difference in execution time. For a handful of tables, classical optimizers can exhaustively check every possibility. But as the number of tables grows, the search spaces explodes. PostgreSQL, one of the most sophisticated open source databases, uses dynamic programming up to about 12 tables, then switches to a generic, in terms of computer science, standard computer science, a genetic algorithm, because exhaustive search becomes impossible. That switch is an admission that we are giving up on guaranteed optimality because of search space is just too large. This is where Quantum Solver proposed to help. Instead of executing the query faster, they aim to find a better execution plan faster, or find better plans than classical heuristics would discover. You feed the Quantum Solver your cardinality estimates, your available operator implementation, your money constraints, and it explores the plan space to propose candidates. The classical execution engine still runs the plan on real data. Now, here's the critical caveat. If your cardinality estimates are wrong, and they often are, even the optimal plan can perform terribly. Quantum does not fix bad statistics, it can only search the plan space more effectively given the cost model you provide. That is useful, but it is not magic. So let me make this search explosion concrete. With some numbers, for 5 tables, you are looking at hundreds of possible join orders, manageable. For 10 tables, you are in the thousands, still feasible, with good algorithms. For 15 tables, you are approaching millions. For 20 tables, you are at billions. For 25 tables, you are in the range of hundreds of millions to billions of possible plans, depending on how you count. This is not a gradual increase, it is exponential. The chart you are seeing shows how quickly this problem spirals out of control. In practice, real production databases routinely handle queries with 15, 20, even 30 tables joined together. Amazon's Query Optimizer, for instance, has to deal with these massive join queries regularly, and the number of theoretically possible join orders is larger than a 10 to the power of 20. No classical computer can exhaustively search that space. You would run out of time before the heat death of the universe. So PostgreSQL, SQL Server, Oracle, every major database system uses heuristics, educated guesses, greedy algorithms, randomized search, genetic algorithms. These work remarkably well most of the time, but they are not optimal, and they occasionally reproduce spectacularly bad plans. The question quantum computing raises is, can we explore this space more effectively without checking every possibility? Physical design tuning is one of the most expensive human activities in database management system. Should you create an index on this column? What about a composite index across these 3 columns? Should you build a materialized view that pre-computes this expensive join? Should you partition your massive table by date or by customer? Every one of these decisions involve trade-offs. Faster queries versus slower writes, reduced latency versus increased storage, better performance for some workloads versus worse performance for the others. These are classic candidates for QUBO style optimization because they are naturally binary decisions with constraints. Microsoft SQL Server has a tool called the Database Engine Tuning Advisor and analyzes your workload and recommends indexes and partitioning strategies. It works by searching through the space of possible physical designs, estimating their impact on query performance, and balancing that against storage and maintenance costs. Quantum approaches could slot into exactly this kind of offline tuning tool. You collect workload statistics overnight, formulate the index selection problem as QUBO, send it to the quantum or hybrid solver, and get back a recommended design. The key is that this happens offline in a nightly tuning job where you have time budgets measured in minutes or hours, not milliseconds. So let me walk you through a concrete scenario that makes this real. Suppose your database team has analyzed production workloads and identified 200 candidate indexes that could potentially speed up queries. That's not unusual for a large application. Different queries benefit from different indexes, but here is the problem. You can't actually create all 200. Each index consumes disk space, slows down writes because every insert or update has to maintain every index, and adds complexity to query planning. Your storage budget might only allow 20 indexes, and your write throughput constraints might tolerate even fewer. Now you need to choose which 20 indexes to create out of 200 candidates. You want to maximize query speedup while minimizing storage cost and write amplification. This is a perfect fit for Kubo formulation. Each candidate index becomes a binary variable, create it or don't. You define an objective function that captures query latency reduction minus maintenance overhead. You add constraints, total storage must stay under budget. Right cost can't exceed your threshold. A quantum annealer or hybrid solver can solve the space of possible index combinations, looking for solutions that satisfy all constraints while minimizing total cost. The solver does not need your raw data, just the statistics about query franchise in terms of frequencies, selectively making a selection estimate or selectivity estimates, and storage requirements. Databases don't run one query at a time. They run hundreds or thousands of concurrent queries with different priorities, different resource needs, and different latency requirements. Some queries are latency sensitive, user requests that need to complete in milliseconds. Others are analytical batch jobs that can afford to wait. The scheduler's job is to decide which queries run now, which get queued, how much memory does each get, how do we distribute work across multiple servers. Get these decisions wrong and you get either wasted resources, too expensive, or SLA service level agreements violations. Catastrophic. AWS Redshift, one of the major cloud data warehouses, has an automatic workload management system that uses machine learning to classify queries and allocate resources. It learns from patterns. Queries that look like this typically need this much memory. Queries from this user group typically have this priority. Quantum approaches could enhance the offline policy generation that feeds these systems. You analyze historical workload patterns, formulate the scheduling problem as an optimization over resource allocation policies, and use a quantum or hybrid solver to find better strategies. The critical points here is offline. You are not trying to schedule individual queries in real time with quantum. That would be too slow. You're using quantum to drive better scheduling policies that classical systems then execute. Now let's talk about something that might seem tangential, but it is actually critical for database infrastructure: cryptography. Most of the public key encryption that secures database connections, things like RSA and elliptic curve cryptography, are vulnerable to quantum algorithms. So that's why the title is post-quantum cryptography, or QKD, quantum key distribution. So do put emphasis on learning this specific slide that is in front of you, is the application area 4. So let me reiterate myself, because this is the most important slide I'm going to share with you in this lecture. So this might seem tangential, but is actually critical for database infrastructure. I'm reiterating myself. There is a reason behind that. This is phenomenal and profound. The cryptography. Most of the public key encryption that secures database connection, things like RSA and elliptic curve cryptography, are vulnerable to a quantum algorithm called Shor's algorithm. If large scale quantum computers become available, and they will eventually be, they could break the encryption that currently protects your database connections, backups, and key management systems. This is not a theoretical concern anymore. It is something security experts are actively preparing for. Every database depends on cryptographic primitives for security. When you connect to a database over TLS, that is public key cryptography. When you encrypt backups at rest, that is using keys protected by public key infrastructure. When you use authentication certificates, that's public key cryptography. NIST, the National Institute of Standards and Technology, has been running a standardization process for post-quantum cryptography, selecting algorithms that are resilient to quantum attacks. Algorithms like Crystal, Kyber, Crystals, Dilithium, and Sphinx, SPHINCS Plus, are designed to be secure even against quantum computers. For database administrators, this means migration planning. You need to ensure your database clients, connection proxies, and key management systems can adopt these new algorithms as they become standardized. This is about crypto agility, being able to swap out cryptographic primitives without rebuilding your entire stack. So this is a realistic workflow that we are now discussing here. So let's get concrete about what a quantum assisted database workflow actually looks like, because this is where a lot of confusion happens. You start by collecting inputs from your database management system, the query graph, showing how tables are joined, statistics like cardinality, estimates, and selectivity, system constraints like available memory and parallelism limits, and workload traces that shows what kinds of queries run frequently. This is all metadata. You are not sending raw data rows to a quantum computer. Next, you build an optimization model. You encode decisions as binary variables, define an objective function that captures what you are trying to maximize or minimize, in reality minimize, like the total query cost, and add constraints that rule out invalid solutions. Then you send this model to a solver, which might be a quantum annealer, a variational quantum algorithm or VQA, or a hybrid system that combines quantum and classical components. The solver explores candidate solutions and returns proposals. Finally, and this is crucial, you validate and apply these proposals carefully. You check that suggested plans are actually correct. You compare them against your baseline performance, and you roll them out with safeguards like canary developments and deployments and fallback mechanisms. This is not quantum runs your database. This is quantum assists your optimizer. The architecture diagram you're looking at shows the reality of how these systems work. It is hybrid quantum classical, not pure quantum. On the left, you have your classical database management system, which holds all the actual data and all the operational knowledge, statistics, cardinality estimates, constraints, workload history. The DBMS sends metadata, not data, to the quantum or hybrid solver. That is the key word, metadata. You are sending summary information about your tables, not the tables themselves. The quantum solver on the right takes this metadata, formulates it as an optimization problem, typically QUBO for quantum annealers, or variational problems for gate-based systems, and explore the solution space. Often there is a significant classical pre-processing simplifying the problem, breaking it into subproblems, making it fit within the quantum hardware's constraints. The solver returns candidate solutions which often go back to the classical layer for validation. The classical execution engine checks these plans for correctness, tests them against known benchmarks, and makes the final decision about which plan to use. The quantum component proposes, the classical component validates, and decides that's the only way to maintain operational trust and debuggability. Here's a trap that researchers and vendors fall into constantly. They optimize for the wrong metric. They'll show you a benchmark proving their quantum solver found a solution in 2 seconds while the classical solver took 5 seconds. And they will call that a win. But that is not what matters in production. What matters is end-to-end impact. Did the total workflow, planning time plus execution time, actually improve? A plan that's 5% faster to execute is not worth anything if it took 10 seconds longer to find. You need to measure 4 things historically. First, end-to-end query latency, the entire time from when a user submits a query to when they get results, including planning overhead. Second, resource usage. Is the better plan actually reducing your CPU, memory, or I/O consumption, input-output consumption, under load? Or does it just shift the bottleneck? Third, stability and variance. You can't trade median performance for unpredictable tail latency. Some plans might be fast on average, but occasionally catastrophic. Force operational cost. What is the total cost of ownership, including the infrastructure needed to run the quantum solver and engineering overhead of maintaining this complexity? If you are not measuring all 4 of these, you are not measuring what actually matters to users and to your business. So let's talk about the reality. Current quantum hardware is severely constrained, and these constraints directly limit what you can do with it. First, there is noise. Quantum computers make errors, lots of them, and these errors accumulate. Every quantum operation has some probability of doing the wrong thing, and the longer your algorithm runs, the more error piles up. This means results need error correction and validation, which adds overhead. You can't just trust what comes back from the quantum computer the way you trust results from the classical CPU. Second, qubit count is limited. The largest quantum computers available today have a few thousand qubits, and not all qubits can interact with all other qubits. There are connectivity constraints. This means the size of problem you can embed directly onto a hardware is limited. If your QUBO or QUBO formulation needs 10,000 variables but hardware only supports 1,000, you have to decompose the problem or use hybrid techniques, which adds complexity and potentially loses some of the quantum advantage. Third, coherence time, how long quantum states survive before they degrade, is measured in microseconds to milliseconds. Your algorithm has to complete before the quantum state decays into noise. These are not temporary limitations. We will solve next year. They are fundamental engineering challenges that will take decades to fully overcome. Second limit, cost models are the bottleneck. So here is an uncomfortable truth that quantum computing does not solve. Database optimizers live and die by their cost models, and most cost models are wrong. If your cardinality estimates are off by the factor of 10, which happens constantly with correlated columns skewed distributions, or stale statistics, then the optimal plan, according to your model, can be catastrophically bad in practice. A quantum solver that perfectly optimizes a wrong model is worse than useless. It confidently gives you terrible plans. There is even a paradox here that makes quantum power a potential liability. A more powerful search method can sometime make this worse by defining plans that exploit quirks and errors in your cost model. Plans that look amazing on paper because they game the model's weakness but fail spectacularly on real data. Classic heuristics often miss these pathological plans simply because they don't search thoroughly enough. More thorough search, whether quantum or classical, exposes this problem. The mitigation is not to avoid quantum, it is to demand robust validation. Any plan suggested by Quantum Optimizer should be tested carefully against real data, rolled out conservatively with canary deployments, and monitored for performance regression. You need the ability to fall back to proven plans if the new suggestions underperform. Debuggability and trust. Database administrators need to understand why the system made the decisions it did. When a query runs slow, the DBA needs to look at the explain plan and understand, why did we use a nested loop here? Why did we choose this index instead of that one? Classical optimizers provide this kind of explainability through explain plans, cost estimates, and traceable decision rules. You can see exactly what the optimizer was thinking, even if you disagree with it. This is critical for troubleshooting and tuning. Quantum and annealing methods can be opaque. You send in a QUBO problem, QUBO, you get back a solution, but understanding why that particular solution was chosen over alternatives can be difficult or impossible. This creates a trust problem in production systems. How do you maintain explainability when part of your optimization stack is a black box? The answer is to keep the quantum component in a proposal role, for not a decision role. The quantum solver suggests candidate plans, but the classical layers make the final choices and provide the explanation. We selected plan X because it reduced estimate costs by 23% under memory constraint Y. The quantum solver explored 10,000 candidates in 2.3 seconds. Classical validation confirmed correctness and performance. This keeps explainability in the classical layer where it can be audited and understood. Here is something that does not get enough attention. Many of the biggest quantum wins in optimization don't actually require quantum hardware. They come from quantum-inspired algorithms running on classical computers. These algorithms borrow ideals along with the ideas from the quantum computing, things like tensor network methods, specialized sampling techniques, and heuristics inspired by quantum mechanics. But they execute on regular CPUs or GPUs. No quantum hardware is needed. No exotic infrastructure, no coherence time limits. For database management system, quantum-inspired approaches can be attractive because they integrate more easily into existing systems, run within the predictable latency budgets, and avoid the operational complexity of maintaining quantum hardware or cloud quantum services. They are also easier to debug and validate because they are deterministic and reproducible. Before you invest in quantum hardware access or quantum as a service subscriptions, you should absolutely benchmark against well-engineered quantum-inspired and classical solvers. In many cases, the quantum-inspired approach running on conventional hardware will give you 90% of the benefit but 10% of the complexity. That is a trade-off worth considering seriously. So let me synthesize what we have covered into actionable insights. First, quantum computing is most plausible for control plane tasks in databases, planning, tuning, scheduling, configuration, not for data plane execution like scanning rows or computing aggregates. If someone promises quantum will speed up their table scans, they are either confused or dishonest. The value proposition is in decision making, not in arithmetic. Second, the best near-term fit for quantum methods is combinatorial optimization problems that databases faces constantly. Join ordering for complex queries, selecting with indexes to create from hundreds of candidates, deciding how to partition massive tables across servers, allocating resources among competing workloads. These are all search problems under constraints and they all scale exponentially, making them natural candidates for quantum or quantum-inspired approaches. Third, practical systems will be hybrid. Classical preprocessing to reduce the problem size and validate inputs, quantum or quantum-inspired solving to explore candidate solutions, classical validation to check correctness and performance. This is not a limitation, it is how you build trustworthy systems. And fourth, the data loading overhead matters enormously. If you need to encode large data sets into quantum data states, the approach is almost certainly impractical. Quantum works when you are optimizing over metadata and not when you are processing raw data. So here are the remaining critical points. Fifth, quantum methods don't fix bad cardinality estimates or weak cost models. They can actually simplify by amplifying their workflows and the flaws by finding plans that game the model's weakness. This means robust validation and conservative rollout are essential. You need canary deployments, fallback plans, and continuous monitoring. Don't trust any optimizer, quantum or otherwise, without verification. Sixth, treat quantum advantage as an end-to-end metric that includes planning time plus execution outcome, not just solver speed. A quantum solver that finds a solution twice as fast but produces a plan that is only 1% better might not be worth the integration complexity. Measure what matters: total latency, resource usage, tail variance, or operational cost. Seventh, post-quantum cryptography affects databases through TLS connections, backup encryption, and key management. Even if you never use quantum computing for optimization, start migration planning now toward NIST standardized algorithms. This is about crypto agility, making sure your database infrastructure can adopt new cryptographic primitives without a complete rebuild. And finally, eighth, always include quantum-inspired baseline in your evaluation. Many quantum benefits can be achieved with quantum-inspired algorithms on classical hardware. Don't pay for quantum complexity until you have proven that simpler approaches can deliver similar results. So what should you actually do with this information? Here are 4 concrete steps. First, identify combinatorial optimization bottlenecks in your own database workloads. Where does your query optimizer struggle? What physical design decisions take hours of DBA time or database administrator's time? Which workload scheduling decisions cause service level agreement violations or SLA violations? These are the places where quantum or quantum inspired methods might help. Don't start with quantum, start with understanding your actual pain points. Second, benchmark quantum inspired solvers alongside your existing heuristics. You don't need quantum hardware for this. Quantum inspired algorithms run on regular computers. See if they find better solutions for your real problems with realistic constraints. Third, start post quantum cryptography migration planning for your database connections, even if you never touch quantum computing for optimization. This is a security requirement that's coming regardless. Audit your TLS configurations, key management systems, and backup encryption to ensure crypto agility. And fourth, measure end-to-end outcomes, not solver performance in isolation. If you do experiment with quantum approaches, resist the temptation to declare success based on solver benchmarks. Measure whether your users' queries actually run faster, whether your resource costs actually decrease, whether your tail latency actually improves. Remember the fundamental insight we started with. Quantum is a tool for specific problems, not a universal database accelerator. Use it where it fits, ignore it where it does not, and always validate the results. That's how you separate hype from reality. So remember, quantum is a tool for specific problems, not a universal database accelerator. Happy learning. See you next lecture.